Hello and welcome back. In this video, we introduce two new concepts, really two variations of the same concept, and these are orthogonal projection and scalar projection. And these are two different ways of answering the question, how much of a vector goes along another vector? So remember when we were looking at work at the introduction for this section, we wanted the amount of force that went in the direction of displacement. So we were answering the question there of how much of the force went along the displacement. In general, the question is how much of a vector goes along another vector. And there's really two ways to answer this question. One, I could give you a scalar and just tell you, really answering the question of how much of a vector goes along another one. So what is the magnitude of the force along the displacement? Or we can get a vector out of this, which is telling me the part of the force vector, say, that goes along the displacement vector. So there's two sort of ways to answer this. This is going to give us two concepts, the orthogonal projection of one vector onto the other. So this is going to be projection of a vector u onto the vector v. This is going to give me a vector. So this gives me a vector. And scalar projection, which is just the magnitude of this projection vector. So how much does a vector go across another one? We call this scale of u onto v. And this is going to be the magnitude of the projection. So this is a vector, this is a scalar, and this is the magnitude of the projection. Okay, so let's work out, first of all, what exactly am I talking about here by vector goes along another vector? Hopefully you have the idea, but I'm going to go through it. And then we're going to come up with expressions for the projection of u onto v and the scalar projection of u onto v in terms of the dot product. So let me jump down here to two vectors that I have plotted. One thing I can do, even in 3 dimensions, is I can sort of rotate my coordinate system, maybe reflect it if I need to get my vector v to be parallel with my new x-axis after rotating the coordinate system, and set it up like this. And so we can reduce our case to just this one where v goes along the x-axis and u looks something like this. Maybe u is over here. We'll talk about that in a second as well. And so how much of u goes along v? Well, this is just like what we did in the introduction of this section. I'm going to decompose u into a vector parallel to v and a vector perpendicular to v. So on one hand, I can measure how much of this vector goes along v. So that is, what is this length here? What is this length? Well, if I have the angle between them, theta, this is just magnitude of u cosine theta. That's this quantity here, magnitude of u times cosine theta, and that is what the scalar projection is. That's what my scalar projection of u onto v is. So there's one way to compute that. If I know the angle between them, all it is magnitude of u. Cosine of the angle between them is the scalar projection of u onto v. So that's great. The other way to answer this question of how much of u goes along v is to return a vector. Which vector am I returning? I'm returning this vector of u onto v like this. So this vector here is the projection, the orthogonal projection, because we dropped a perpendicular or an orthogonal down, of u onto v. Okay, so we're going to work out what these are. Keep in mind that u dot v is u v magnitude v times the cosine of the angle between them. My scalar projection of u onto v is u cosine theta, so that's this part. And so really u dot v is the scalar projection of u onto v multiplied by the magnitude of v. And so what that means is then I can solve for the scalar projection of u onto v. You can think of this one way to remember which one's u, which one's v, which direction am I going here. U is sort of the bigger one, v is the subscript, u is going on to v. It's sort of below the u. So the scalar projection of u onto v then is going to be u dot v. Remember, that's a scalar over magnitude v, another scalar. So this is division of real numbers here, and that gives me my scalar projection, which works out to be a scalar. So that's not too hard to compute once we have the dot product. And remember, we have this other form of the dot product that doesn't involve the angle. So I don't have to figure out the angle between the two vectors in order to find this scalar projection of u onto v, now that I have this other form of the dot product. So that's pretty cool. I want to definitely keep that one in mind. And then how do I get the projection? Well, the projection, like I said, the magnitude of the projection, the orthogonal projection of u onto v, should be this scalar. That's how we're defining this scalar projection, is the magnitude. So I know I want that, and I also know that the projection of u onto v needs to go in the direction of v. So I want to say in the direction of v. And what's cool about this this theory that we're working out here is this is our first time that we're seeing how we can use this idea of a unit vector in the direction of another vector as the direction of v. So what I mean by that is, how do I obtain this vector projection of u onto v, knowing its magnitude? So we have the magnitude, so magnitude of projection of u onto v is the scalar projection, which we have an expression for already, right? That's our u dot v over magnitude v. And then in the direction, so the direction of the projection of u onto v is in the direction of v. And remember, one way I can specify the direction of a vector is to give you a unit vector that's parallel to v. So this direction then, I can write this as in the direction of v scaled by the magnitude of v, right? So this is a unit vector in the direction of v. That's also the direction of projection of v onto u. And so what that means then, once I have magnitude and direction, is I can take these and I can say, okay, well then the projection of u onto v is, well, the magnitude is u dot v over magnitude v, and then in the direction of v over that. So that is, I'm scaling this unit vector to the appropriate magnitude that I want. So times v over magnitude v. So that is, this part is the, let me do it up here. This part is the magnitude times the direction. And simplifying this a little bit, so this is u dot v is a scalar, magnitude v is a scalar, magnitude v is a scalar. So what I have is a bunch of scalars scaling my vector v. So I have u dot v over magnitude v times magnitude v scaling my vector v. So here I have a vector, and this is a scalar. Now magnitude v times magnitude v, that's magnitude v squared, which, if you remember from an earlier video, is magnitude, or is v dot v. So what this really is, and this is a really awesome form for this, is u dot v over v dot v. That's a scalar, and that's scaling the vector v. So this is telling me it's going along v, scaled by this much, and that's my projection. So u dot v over v dot v, scaling v, is this projection vector. So these are going to be pretty useful things to work with. This projection, like I've already shown you how, if we're say pushing a block and our force is not parallel to the direction of motion, we want to decompose it. So the scalar projection and the orthogonal projection are ways of decomposing vectors, or really what they're doing again is telling me how much of a vector goes along another vector. Either want the scalar version of that or the vector version of And here are nice expressions for those in terms of dot products. All right, I will see you next time. We'll put this to use with an application.